We are considering a uniform disk scenario now. We are figuring out the moment of inertia of this uniform disk. So now we are considering that it's to be rotated along this axis, which is perpendicular to the plane. So we are considering a uniform disk of mass m and radius r. So this is radius r rotating about axis that is passing through the center and is perpendicular to the plane. This is the scenario. Now center, I'll consider this as O. Let's start off. So obviously we are going to make use of I is equal to r square dm. So we need an expression for r and dm. It has to be a single variable. So for that, what will I do is, let me go to this animation. So we have the disk. I will consider small concentric rings and their radius is x and the width is dx. So if I consider this, then I need to integrate from the smallest possible value, that is a dot, to you keep expanding to a value of r, 0 to r. Can I repeat? So we are considering a disk, and how do you integrate all of this? How do you add up all of this? How do you add up all the moment of inertia of all of this part? For that, we start off with a ring. So ring gives us the constant set of value of x. The width of this ring is dx. So now this x has to vary from the smallest of value 0 to the largest of value, in this case r. So let me explain it this way. So for above integration, it will be convenient. Sorry, this is, yeah. So it would be convenient to divide the disk into many concentric ring with a center as O. So basically what I'm trying to put over here is, so we are considering a small ring something like, no, not that actually. Let me do this. Yeah, that would be better. Cut, paste, and we have this to be the center. This is of radius x and width is dx. Okay. Now, out of all of this, what we'll do is, we'll consider one such ring of radius x and width dx. Then what are we looking at? Then r will be x, right? The radius will be x, and the mass, right? We are getting expression for r and dm in terms of a single variable. So basically we're looking at x and dm. So for dm, we are looking at mass being equated to density times the area. So here the density will be equal to, total mass divided by the total area. So that is pi r square. Therefore, a small section of mass dm, will be equal to m by pi r square. And what is the area of this thin ring? Well, thin ring length will be 2 pi r and width is dx. Right, we have considered the width to be dx. And the length is a circumference. So we have 2 pi, not r, sorry, 2 pi x. The radius is x over here. Okay, so please understand this. If I expand this thin ring, so it will be from 0 to 2 pi r, right? It would be something like this. We have already seen this. It would be something like this. We have a thin ring, and when you expand it, it will be from 0 to 2 pi r. So this is a very thin ring, okay, and that is represented with, the width is represented with dx. So basically this is length into breadth, that gives us area. So we have pi and pi getting cancelled, and let me not continue this further. So you can imagine me simplifying this. So when we substitute in I, we have I is equal to integration of r is x square m by pi r square into 2x dx. Okay, so is that right? Looks so. Okay, anyways, just a matter of rearranging and this looks a bit messy though. Now this looks better. Oh, sorry, there's no pi. My bad, pi got cancelled. Now, oh sorry, we are integrating from what to what? We are integrating from 0 to r. This we saw from this animation. So this small ring has to vary from a dot to a length of r, to a radius of r. And so we have this to be integration of x cube, so x into x square into x is x cube. So x to the power of 4 by 4. Okay, and this is from 0 to r. So this will be 1s are 2s are, so we have 1 by 2 m by r square, and this will be r to the power of 4. So this and this will get cancelled, and we have I through the center of mass with all of this condition, half m r square. That's it. If I pick up a case wherein the axis of rotation is moment of inertia with axis of rotation, next obvious case will be tangent to the disk and parallel to axis that is perpendicular to disk and passing center of mass. So we are to make use of correct parallel axis theorem. Okay, so with parallel axis theorem, all we are doing is we are shifting it to this point. So I'm not able to show it over here, so I'll do it here. So we have the disk Not a good one. So we have the disk. We shifted the center from here to here. So this is, say, the original one, AB. This is what we're looking at. A dash B dash is what we have. And this is perpendicular to the plane. And these two are parallel to each other. So as per this, you have I through AB will be equal to I through A dash B dash plus md square. M is the total mass. And here M is, sorry, not M, D is R, right? So it has shifted with the distance of R. So we have IAB is equal to half mr square plus mr square. So this, all of this will be 3 by 2 mr square. And that's that. Okay. So we are rotating in this manner, so on and so forth. So then we have case moment of inertia with axis of rotation along a diameter. So here we are making use of, yes, we can make use of perpendicular axis theorem. So same stuff, I mean same diagram actually. So we have one diameter, another diameter, they are perpendicular to each other. We have PQ, P dash Q dash. Say through PQ, I'm rotating in this manner. Clockwise or anti-clockwise, whatever you guys want to think of. So using perpendicular axis theorem. So moment of inertia through PQ plus moment of inertia through P dash Q dash should be equal to moment of inertia through A dash B dash. Here I PQ will be same as I P dash Q dash, as both of them are via diameters, and therefore we have 2 times of PQ is equal to, this is, we already know this would be 3 by 2 mr square. And so a bit of rearrangement, and we have 3 by 4 mr square. So same thing, if I shift, let me do it off here. Same thing, if I shift my axis to moment of inertia via or moment of inertia with axis of rotation along, with axis of rotation along. So let me think of it along tangent to the disk and in the plane of the disk. So basically this would be a top view. You have this supposed to be a circle actually. So we know about the moment of inertia along the diameter, and now we're looking at a line like this. So we have AB, so we have A dash B dash through the center O. So we have moment using parallel axis theorem. So moment of inertia along AB will be equal to moment of inertia along A dash B dash plus md square. Here d will be equal to r. There is a shift of r. And then we have IAB is equal to, this is 3 by 4 mr square plus m is m r square, and you do the math. So this will be 7 by 4 mr square. And that's that. Okay, guys. So what is the funda? So funda is that we have to consider a small ring and then integrate it. That's it. That's how we start off with. So let me just verify every result. Half mr square. Then we have from there 3 by 2 mr square. Okay. And here we are making use of, oh, if this changes, then quite a few things changes actually. This is half mr square, right? This is half mr square, not 3 by 2. So half mr square, so this will be 1/4. This is 1/4. This will be 5 by 4. 5 by 4 mr square. Okay. Then yeah, that's it. See, it's not that you need to by heart. Honestly, if you understand the derivation first, then memorization will become easy. So I always advise this. You guys have to follow it. There's no option. That's why I keep talking about it. These two are parallel. That's the diameter.